Okay. Okay. So we're going to start with chapter 1 of this book by Hoffman and wait, I'll tell you. I think it's Kunze, but I don't want to. I'll send you the spelling. Okay, so it's Hoffman and Kunze, basically, called linear algebra, and we're going to look at the first chapter, which is linear equations. Okay. Okay, great. So let's start with the first section of this chapter. It talks about fields. Okay. So a show of hands for anyone who's seen fields before in some context. So you guys have some familiarity. Okay, so you'll probably get a little bit bored, so be a little bit patient, okay? And then we'll see what's happening. Okay, so the point here is that it is sometimes helpful to describe key properties of real and complex numbers, okay, using more abstract properties. Okay, rather than looking at real and complex numbers directly, we abstract out the relevant properties. And one such abstraction is called a field. Okay, so story abstract out. Also, I should say that my handwriting can be a little bit illegible sometimes when I'm writing too fast. So stop and tell me and I'll fix it. Okay. Okay. So abstract out relevant properties of real/complex numbers. Okay. Great. So the way we do it, so here's a formal definition. So I'll give the definition. It's fairly intuitive. Okay. So suppose that F is a set. So let F be a set. Okay. And suppose two operations, which we'll call addition and multiplication, are given by the symbols plus and dot for multiplication. Okay, so these are just symbols for the moment. Okay, so these are operations that take two elements from F. Okay, two elements from F. For some reason that's too much. Into an element of F again. Okay, so it takes two elements. So for example, with real numbers, we know, right? You take two real numbers, you add them, it gives you another real number. Similarly, multiply two real numbers, it gives you another real number. So that's sort of, but we're saying abstractly. Okay, so suppose these are two arbitrary maps. We don't know what they are. Then we say that F, comma, plus, comma, dot. Okay, so this triple is a field if the following conditions are satisfied. Following are satisfied. Right. So the first condition is that addition is commutative. Okay. So who wants to tell me what commutative is? You must have seen this before. Speak up. Yeah. Exactly. So suppose the elements are x plus y. So suppose the elements are x and y. So this basically says that x plus y is equal to y plus x. Okay. All these things will look very stupid, okay, because these are completely true for real numbers and complex numbers. So they're going to look a little bit silly, but the point is that somehow these are all the properties we need to make reasonable conclusions later. Okay. Second property we need is that addition is associative. Okay, so what does this mean? Exactly. So because we're using x's and y's, let's just use x and y, but yes, that's the same idea. So x plus y plus z is the same as x plus y plus z, right? For all x, y, z in the field. Okay. Also, I'm guessing you're all familiar with this, but this is like the belongs to symbol, right? Yeah, if there's something which is unclear, let me know, okay? Because I know people come from different backgrounds. So yeah, just ask if it's needed. Okay, the third point is that there exists So there exists, which we sometimes write as there exists like that, right? A unique element, which we denote by 0, okay, which we call 0, such that 0 in F, sorry, I should write 0 belonging to F, such that, so what is the key property of 0 in terms of addition? Yeah, how would you capture? Exactly. So yeah, so x plus 0 gives you x, right? Well, that's like if it's true for all x, then we say it's essentially 0. So note that I'm using the same symbols because these are suggestive, okay? But in general, they could be something more abstract. Okay, so if any element is such that when you add it with any other element of the field and you get exactly the same element, then this element is what I will call 0. Okay? So that's the point. All right. Number 4, you will see some strange things as well. Okay, so that you know, you can have fields with like non-zero characteristics and things like this. So you can add a bunch of ones and it will give you 0, which doesn't happen with real and complex numbers. So I'm just emphasizing these things so that you know that even though they're very similar, they are more abstract. Okay, so they can be more general depending on what is needed. Okay. Now for all x's in F, there exists a unique element that we call minus x in F, just to be intuitive, such that x plus this element, which is minus x, gives us 0, where 0 is what we defined above, right? Is that okay? Okay. And the 5th point is that multiplication is commutative. Okay. These are a little bit boring and dry, I know, but we'll do fun things soon, I promise. Okay. So xy equals yx. That's commutative, right? Basically how we define for addition, right? For all xy in the field. Okay, perfect. The number 6 is multiplication is associative. All right, somebody wants to tell me what this is based on what we've seen so far? Not somebody who's answered before, okay? Somebody new. Exactly. So x times yz is the same as xy times z, right? For all x, y, z in the field, right? It's basically following what we did for addition, right? So for addition, remember we had x plus y plus z, right? And we said whether you do this, it's the same as if you do x plus y plus z, right? So it's essentially the same idea. It doesn't matter which order you do the operation in. So that's what is meant by associative. Okay, so let's take this out for now. Fine, using the tablets, I can erase it easily. Okay. So number 7 is, so now here's the analog of the inverse, right? So there exists a unique non-zero element. Oh, sorry, this is the analog of identity. 1, okay, in F such that, okay, so now we want the identity for multiplication. So what should I write here? X into 1 equals x, exactly. Yeah, so x times 1 is x for all x, just like how we define for addition, right? Okay. The 8th property is, this is the inverse, right? So to each non-zero x in F, there exists a corresponding. Also, I have to admit I'm bad with spellings. Okay, so if you correct my spellings as you go along. Unique element x inverse or 1 by x in F, okay, such that, so this is just, you know, a notation we're using for that specific symbol or that specific element, sorry. And what should it satisfy? Yeah, what should it satisfy? Yeah. So this one is completely trivial, it's just standard algebra. Okay, and then finally we have multiplication is distributive. You can ask me, okay, if you have any questions, feel free to directly ask me. Because if you speak among yourselves, then very quickly it becomes very difficult. Okay. So multiplication is distributive, and what does that mean? It means that x plus y, sorry, y plus z is xy plus xz for all x, y, z in F. Is that okay? All right. So it turns out that these are all the properties we need. And now let's build some intuition, because that was the formal definition. So like I said, intuitively we define them so that so fields are defined to mimic properties of the real numbers. Properties of reals and complex numbers. Because I'll use this for numbers. Okay, I'm a little bit lazy, but I hope you follow. You can understand. No, this is supposed to be like a longer preview, so we can refer to things as we go along. Okay, all right. So this is fine. Another thing maybe to mention is that we're going to call such things. So elements of the field are going to be referred to as elements of a field are going to be called scalars. Yeah. All right. Right. So the first note now is that this is sort of something very, very easy to check, right? That the set of real / complex numbers form a field with respect to standard addition and multiplication. This is completely trivial, right? Because we used all the properties. So there's nothing new. Okay. So far, it should be very boring and straightforward. Yeah? Okay. All right. So let's continue. So now what we're going to do is we're going to define subfield. Okay. So we now define subfields. So subfields are basically supposed to be intuitively a smaller field within the bigger field. Okay, just as the name suggests. Okay. So what is the formal definition? So the formal definition is the following. So let F plus and dot be a field. Okay. Then F prime plus and dot. So note that I'm using the same operations. Okay, I'm just changing the set. I'm using the same addition and the same multiplication, but I'm just changing the set. Okay. Then this is a subfield of F. Subfield of F plus and dot if F prime is a subset of F and F prime plus dot is also a field. Okay. Does the definition make sense? Yeah. You can take a minute, make sure that you're following. Right, yeah. Okay, so given everything I've described so far, can you think of an example of a subfield? I haven't discussed much. Exactly. Excellent. Exactly. So that will come a little bit later, but from what I had covered, we already have an example, right? We already have that real numbers are clearly a subfield of complex. Yeah. It should be, yeah. But at least it satisfies the definition. It satisfies the definition, right? Yeah. So it should be okay. Yeah. Is that okay? All right. So yeah. So here, as wait, what was the name? I actually should write down some of the names at least, so I can keep track of who's being. So who answered? Can I spell it as TEJ? Okay, perfect. And who are the people who answered so far? Can I get your names? Bharat. Okay, Bharat. Is that correct? PH. Okay. Who else answered? Akansha, Arusha. Okay, I'm sorry, I'm bad with names. Arusha. I'm probably going to butcher the spelling. Arusha. Arusha. Okay, good. And who else? There were a few more people. Masood, R, D, Masood, like that. Okay, okay. So sorry. Okay, I'm really bad. Also, it's a little bit hard to hear from here. Okay. Is there anyone I missed so far? Tanisha. Tanish. Okay, okay, nice. Yeah, I'm just writing this down so I kind of know who I'm talking to. That's all. There's no other reason. Yeah, it's just okay. And so you guys also know who to bother when you have doubts. So you can go and talk to these people. Should be good. Okay. All right. So the next note is that the set of reals is a subfield of complex numbers. Okay. All right. So there's a little remark about notation, which is that sometimes we are going to use, we will use f instead of, writing the entire tuple f times dot. Okay, just for brevity, it's easy. Okay, all right. So now the usefulness of this notion of subfield arises from the following fact, which is that we are normally okay. So we focus here. Okay, we focus on subfields of complex numbers. Let me just write C, okay? So I'll use C as the symbol. Sometimes I'll try to be consistent, okay? Sometimes but I tend to be a little bit sloppy, okay? So these are both complex numbers. Okay, so in almost the entire rest of the course, we can assume that we are looking at subfields of complex numbers. Okay, that's the requirement. Okay. All right. So we already saw that we have a we saw some examples. Maybe I can give you one or two more. So okay, so let's look at this example. So we have a set of positive integers, 1, 2, 3, and so on. Okay. Okay. Is this a subfield of C? Somebody said no, but if you've already answered, don't answer anymore. No? If it's too stupid, you can just raise your hand and tell me. It's okay. I know it's very straightforward. Or if it's not clear, even then it's okay. Exactly. So it's not even a field, right? So it's not even a field. Yeah, we can do this. It's probably fun. What's your name? Amika. Oh my God, just spell it. Is that what? Okay. Okay. That's fine. Good. So let's look at the next example. So this was example, I suppose, example 1. Let's look at example 2. Okay. The set of integers. So we're going -2, -1, 0, 1, 2. Okay. So is this a subfield of? You already answered no. You haven't. Okay, tell me. Exactly. No multiplicative inverse. Right? Like, for example, what is the inverse of multiplicative inverse of 2? It's not in the set. So what was your name again? Who answered? Ashwin. Ashwin. Is that all right? Example 3. Okay, it's clear, right? If something's not clear, just ask me. I'm just going through very, very simple examples. It's the first class, so let's make sure everyone's on board. The set of rationals. Somebody had mentioned rationals, so the set of rational numbers. Okay, is this a subfield? Okay, so somebody had answered. Can you remind me your name again? Oh yeah, with the U, right? Okay. Is it clear why? So it solves all the problems, right? This also has multiplicative inverses because it's of the form P by Q. So everything will have an inverse. Let me check that. Okay, and obviously, if you add, subtract, multiply, or divide rationals, it's still a rational number. Nothing changes, right? And it is obviously a subset of complex numbers. So this is okay. And in fact, one can show that every subfield of complex numbers, okay, must contain the set of rationals. Right? I mean, it's kind of obvious, but it's still nice to note. Yeah.
Say the set of rationals in the subfield. Is it okay if we is it done? How do we mention every time we should add the set of rationals?
Okay. Can I bring your attention to point 8?
Oh, okay.
Okay, good. Okay, I know, but that's a good point. So these things are formalized such that all these subtleties are already handled. And that's the whole point. But that's a good point. Mm-hmm. Yeah, is it? Yeah, you need -1. That's true. Yeah, but then you can build 2, right? Then 2 will not be, because you can do 1 minus -1. You can subtract -1 from 1, and then you're not even a field, right? Because it at least has to take life. That's a good point. Yeah. Any more questions? Then you don't have the like you need to have a one element, right? It said that there has to be a non-zero element. You don't have the multiplicative identity then, right? So it doesn't satisfy the axiom. Where is it? So what? Huh? You have to speak up a little bit. I can't hear you. So you can build your own axioms if you want, but these are the axioms we follow. Okay. All good? Wait, what? Complex numbers can only have one subfield, which is the. Where does it say that? No. The statement was different, right? You mean this one, the one I wrote about rationals? Yeah. Yeah. So read the statement. What does the statement say? Okay. And is it the same as what you said? What did you say? I'll write down what you said. Right. So let's clarify this. So C has only one subfield, which is the set of rationals. Okay. And you think these two statements are the same? That's the confusion. You think that these statements are equivalent. We just saw, right? Real numbers. Real numbers are not rational, right? And they're still a subfield of complex number. Right? Yeah. So these statements are not the same. Okay. Even logically, even if you did not know a counter example, do not make the mistake of thinking that these are equivalent. These are different statements. Say it. Sorry, louder. Yeah. Only one. Yeah. Only one. One subfield. Exactly. So that's the point. Yeah, sure. The statement is wrong because this is false. I was just trying to clarify what was said by. What was your name again? Manoj. So that's a good point, right? Like you have to be careful about only and all these things in math, right? These are like all it's saying is that whatever subfield you construct of C, it has to have as a subfield, or it has to at least contain the rationals. That's all it's saying. So it cannot be smaller than the rationals. That's all. Okay. All right. Okay. And let's look at another example. So example 4 is the set of all. Yeah, just a second. Let me finish writing this. Complex numbers. Sorry, yeah. Multiples of I, well, you'll get -1 and things like this. Yeah, you could probably do it. Like one would have to check. You just have to check that the axioms are satisfied. That's all the game is here. So I don't want to say something wrong on this form, but so yeah. So then it's probably wrong what you're saying. No, because probably you can multiply I by with itself, right? It'll at least give you the rational somewhere. That's fine. Okay. So example 4. I should have asked you. Okay, is this a subfield? But it already said. Okay, you can check this. You can. I'll leave it as an exercise that this funny looking thing, this set for all xy is going to form a subfield. Okay. All right. So that is fine. Yeah, I should say that x and y. Yeah. Let's see. Are rationals. Yeah. Maybe I didn't mention this. Thank you. That's a good point. I forgot to qualify the thing. Of course, because if you put x and y as complex, then obviously then the whole thing just becomes complex, right? Then there's no. Yeah, you can put irrationals, it will cause problems. That's why I'm saying, yeah, you have to take x and y to be rational. Yeah, that's a good point. Thank you. Yeah. Where is that? That's 2. Yeah. 2. Yeah. So the thing is, okay, just for clarification, when I write z, if I write little z, I'll make it like this. If I write a capital Z, I'll cross it like that. Okay. So whenever you see a symbol like this, it's 2. It's just for clarification. Okay. Any more questions? Okay. All right. So earlier I said something, right? I said that, so we'll assume, remember the assumption. And the assumption was that we restrict to subfields of complex numbers. Okay, but why, right? What is the motivation behind doing this? And it turns out, and this we'll not dwell into too much, it turns out that there are things called fields of characteristic n. Again, what that means is that so it can happen that in some field, say L prime, 1 plus 1 plus 1, this is like n many times, okay, gives you 0. Okay, so it doesn't violate any of the axioms. You can do this. Okay, and then this causes issues with the kind of discussion we're going to have. So for now, we're going to assume that we are looking at, and obviously with complex numbers, you can't do this, right? Like you can't add 1 finitely many times and get something 0. That just doesn't happen with complex numbers. So therefore, we are going to restrict to subfields of complex numbers so that things are sort of well behaved in this. It's just a small little caveat. All right. So that completes the first section. Oh no, I ran out of space. Okay, let's see. Okay, I can just go sideways. All right. So now we're going to look at the next section. Section. So this is section 1.2. Systems of linear equations. Right. So the definition is the following. So suppose F is a field. Okay. A system if you guys have any questions, you can ask me. Okay, please don't talk among yourselves. If you need to ask something, you can ask me. If you're not interested, read something. Okay, just don't talk among yourselves. That's all. I'm sorry, it's just difficult for me to concentrate. I know some people can do it and then they work well. It's just, yeah, for me, it's just a little bit difficult. Okay. Okay, so a system of m linear equations in n unknowns is any problem of the following form. Okay. Find n scalars elements of F. Okay, so x1 to xn, such that it's just a pretty standard definition. A11 x1 plus A12 x2, A1n xn equals y1. Okay, and the same thing for m different rows. X2. Okay, is the definition okay? Oh shoot, I didn't complete the definition. That shouldn't be okay. Where y1 to ym and aij, where I goes from 1 to m and j goes from 1 to n are, okay, we have to complete our what? What would you guess it to be? Huh? Anyone else? Exactly. So the elements of F. Okay. This is good? Making sense? All right. So we're going to call this equation 1-1. Oops. Okay. Right. Now we're going to add a few more things, right? So any n tuple going from x1 to xn of elements in F satisfying each equation is called a solution of the system. Okay, so sometimes we'll omit writing of the system, but that's what it is. It's fairly reasonable. Okay, it's just nomenclature. And if y1 equals y2 equals ym equals 0, the system is called, you guys must maybe know this word. It's called what? Homogeneous, exactly. Yes, the system is called homogeneous. Who said that? Okay, can you tell me a name? Oh shoot, I forgot. With the D, right? Is that it? There's an E somewhere? Is it correct? Ah, okay. 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 Any questions about the definition? It's just basically a set of equations, right? That's all it is. If all the y's are 0, then it's a homogeneous system of equations. And if you find the x's that solve this equation, we call them a solution to the system. We haven't done much. Just wrote it down clearly. That's it, because it'll be useful later. Okay. All right. So we have the definition. One natural question one might ask, of course, we want to solve the system of equations, right? That's one of the main things. But one simpler question one might ask is that if I give you two different systems of equations, can you say that they are the same? Can you say that the solution set is the same? Okay, so that's one natural question one can ask. So can one determine whether two distinct systems have the same set of distinct systems have the same set of solutions. Okay. All right. So what we'll do is we start with an illustration. So start with an illustration. What is the illustration? So suppose we want to solve the following. So we have 2x1 minus x2 plus x3 0. Yeah, you guys, I should also silence my phone. That's true. Okay, give me a second. Yeah, you can also take a minute and silence your phones. It's on. Okay, so suppose you're given this, right? And then x1 plus 3x2 plus 4x3 is 0. Okay, so this is the system of equations homogeneous. Yeah, just by definition, right? Y is a 0. Okay, good. So this is what we're trying to solve. And okay, so what one thing we can do is we can, like this stuff you already know. Okay, I'll just do it. -2 times second equation to first, right? And you'll get -7x2 minus 7x3 0, which is equivalent to x2 being minus x3. Right? So far I haven't done anything. It's very basic. You've done it like a million times. And then you can add 3 times the first equation to the second, right? And you will get, and you can check, okay? I mean, I'm also not checking explicitly, but it's very simple to verify. Okay, so 7 and Z might start looking the same, okay? Sorry about that. If my handwriting gets bad, tell me, okay? This is hopefully, you can understand it, what I'm writing? Yeah, okay. Everyone? Okay, okay. So then x1 is the same as minus x3, okay? And so what do we conclude? Okay, so obviously the calculation is not really the big thing. So what we conclude from this is that if you have a solution to this, right? So let's say, so suppose x1, x2, x3 solve, so this is to 1, okay? Then they must also satisfy x1 equals x2 equals minus x3. This is obvious because we, if it solves it, then obviously if you add subtract them, that'll also be a solution, right? So whatever conclusions we drew from adding subtracting them will also hold, so that is fine. And conversely, one can check that a comma minus a is a solution to the system of equations. Okay, I can just say a is a solution to 1 since we already wrote it down. Okay. So why are we going through this example, this very, very simple, trivial example? We're going through it because somehow it seems that, the set of solutions to number 1, and let's call this number 2, right? So it looks like the set of solutions to equations in system 1 and in system 2 are the same, right? Because we showed both ways, right? So now what we want to do is we want to generalize this intuition, right? Which is what math is all about, right? Like we're going to try to abstractly figure out what is happening. And okay, let's see. Okay, so to do this, what we're going to do is we're going to start with linear combinations system. Okay, so to formalize this idea, formalize this method of showing two systems have the same solution, we define linear combination. So linear combination you already know, but let's just write it down properly. Because if we are clear here, then later things would become easier, right? So we recall, what we had in the previous definition, and we had defined what. So previous definition meaning the definition of. Oh yeah, I should use the second thing here. So the previous definition meaning this thing, right? So we had defined a system of equations. I'm just asking you to recall this system of equations, the definition over there. And the definition of 1, 1 in particular. Okay. And now suppose so suppose that one selects scalars C1 to Cm, okay, multiplies, okay, and we multiply, or one selects, okay, so when one multiplies the jth equation with Cj, okay, and obtains C1 A11 plus, okay, let's just directly the last one, so Cm Am1, okay, x1 plus C1 A1n plus Cm Amn xn. Okay, so what you're doing is you're basically picking these. Oh, you probably can't see the. Can you see the pointer thingy? The little eraser on the board? No, probably not. It's not kind of resolution. Okay, so basically you're picking out individual. Why is it not hiding? Okay, so one can pick out individual equations from here, right? Multiply them with C. So you multiply with C1, and you add them up, Okay, and then you can rearrange and write them like this. And that's all I've done. Make sure you're following, okay, because this is not mysterious at all. It's very straightforward. Okay, and this has to be the same as, yeah, tell me what the right hand side should be actually. If you understand it, it should not be too difficult to write the right hand side. So what I'm saying is you multiply the jth equation with Cj, okay, and you sum them all. Okay? So what should the right hand side be? So I've written the left hand side of this procedure. No, you've answered. Okay. And anybody who hasn't answered before. Okay, so this is what we're doing. We are selecting these scalars, right? And then we're multiplying the jth equation here, right? So this is the first equation, the second, so forth. So the jth equation is being multiplied with Cj, and we're summing them. Okay. Okay, I should write and sum them. And sums them to obtain. Come on, you guys. Well, what's the confusion? Tell me, where are you stuck? Tell me your thought process. How far have you thought? Where are you stuck? No, talk to me genuinely. I mean, I'm not trying to scare you or anything. Just have to make sure you're following. What is so we're just taking this equation. What's that? Okay. Wait. Okay. Tell me. Exactly. Thank you. C1y1 plus C2y2 all the way to Cn y. Oh, M, sorry. Right, because there's MYs. Is that okay? They should be super duper clear. We're not doing anything at all. Okay. So if something's not clear, I encourage you to pause. The whole point is that you learn. Okay. So if you're getting lost, this thing is going to build in a sequence. If you fall off at some point, the rest of it is not going to work. Then you'll just get bored and it will sound very, very complicated. Okay, so I urge you at any step, if something is not clear, you stop and you ask me. It is okay. We are recording everything. If we are not able to finish things on time, I will record the lectures. I'll give you the remaining things so we don't lose space. But at least in class, you have to make sure you're following. Okay. So please do ask. Okay. So what does this mean? Okay. So such a so this is what you get right by that procedure. And what we were doing was we were writing a definition. Okay, so what is this definition defining, for lack of a better word? It's defining a linear combination. Okay, so such an equation is called a linear combination of equations in 1, which is the equations in this matrix. Okay, that's the definition of a linear combination. All right. Okay. All right. So here's a quick question for you. Is a solution to 1 also a solution to uh, uh, the equation above? Anybody who hasn't answered? Okay, sorry, maybe you can't see the screen. Sorry, forgive me. Yeah. So basically what I'm asking is that suppose you have some x1 to xn, right, that satisfy this the right hand side. Okay, sorry, that satisfy this all these equations. Okay, do you think that would also satisfy this equation? Perfect. So the answer is yes. Okay. All right. So now we can use this idea. So the story now is that, so we will use this idea and use this to generalize or to define, sorry, a notion of equivalence, to define a notion of equivalent systems. Okay, and how we do this is the following. So let's push that away for a bit. So recall again this 1, 1, right, which is on the right hand side, and consider. Somebody said something. Sorry. Okay. Yeah, just speak a bit louder if you need my attention. I'm a little bit struggling a bit with hearing you guys. Okay, so consider another system of equations. Okay, and the other system of equations is b11 x1 plus b1n xn equals z1. Okay, bk1 x1 on the way to bkn xn equals zq. Right? So these are the system of equations. So we say that these two systems are equivalent. These two systems are equivalent if each equation in each system is what? Okay, the computer gave up. Sorry about that. Don't know what happened. Okay, where are we? Right. So if each equation in each system is, oh, I'm so sorry, guys. Sometimes it's the first time I'm using this for teaching, so I'm not. Seems to be okay. All right. Each system. So each equation in each system is a linear combination of the other. Well, I should say, okay, linear combination of equations, to be more precise, of equations in the other system. Okay, so is the definition clear? So let's go through the definition. The definition is basically saying that, suppose we pick the first equation here, okay? We should be able to obtain this equation by taking linear combinations like we did in the example of the linear combination of equations in A. One was the one with A's, right? Is that okay? Or do you want me to, let's see if I can open another window. So this is the B thing, and then this is the A part. Right here. Okay. So what we're saying is that this B is a linear combination of equations on this set. Okay, so each equation is some linear combination. Okay, and the other way. So each equation here is a linear combination of equations here. Okay, if that is the case, then we'll say that the systems on the the A system and the B system, they're equivalent. Is the definition okay? Yeah. Tell me. If something's not clear, tell me. Oh, okay. You can ask, okay, if you have any questions, there's no. Okay. Okay. Does anyone have any intuition for why we are defining equivalence this way? Why would we define this notion? Uh-huh.
For one system, the equations, maybe a combination of equations in the system. That's it, like one works. The other system, really.
No. For example, you could take just like the same equation so many times, right? Nothing stops you from doing. Okay, so the question was that is it really necessary to say that both ways? Like, is it not enough to say that B is a linear combination of equations in A? It's not. It's not enough because, like, for example, you could take the same equation n times, right? That is still a valid system, and of course, that doesn't capture all the other equations.
It's not necessarily that both complex systems have the same number of equations.
Yeah, that is. I mean, for now, I think we are assuming that it is, but in general, it doesn't necessarily have to be. Like, for example, you could repeat a few equations, and that shouldn't change anything. Is this okay, you guys? Okay. Does anyone have any intuition for why we are calling this equivalent? Before I actually tell you why it's called equivalent, but do you have any intuition for why this is a good notion of equivalent? So what was the question we were trying to solve here in the beginning? We were trying to understand when two systems would have the same set of solutions, right? And now we came up with this notion of equivalence. Exactly. So this is what we will eventually prove, that if two systems are equivalent, then the set of solutions they have will be identical. Okay. And this almost follows from what we've discussed so far, right? Because we said that so if B is satisfied, for example, and A is a linear combination of B's, then we know each A is satisfied, right? Just as we argued before. And similarly, the other way. So I'll write it down. Don't worry. This is going quick. I just wanted to make sure that you have the context for why we are defining things the way we are defining them. Okay, good. So, oh no, that's he doesn't give more details of the proof. Okay, so you have to go and think about this. Okay, so I'll just write very informally. I'll write what the idea is, and then I'll write the theorem, and you can make sure go home and think about it a bit to make sure you understand. Okay, so clearly, if the systems are equivalent, and x1 to xn is a solution to the first system. Yeah, let me just be a little bit more brief. So I'll write to 1. Okay, so 1, should I write 1? Yeah, let's call this 1, 2. Okay, so is a solution to 1, 1. Then it is also a solution to each equation in 1, 2. Okay, so here what we're doing is we're essentially running exactly this argument that we did, right? So in this illustration, oh sorry, not this illustration. Yeah, so we had this note, right? So this note, so NB. Okay, so what was this note saying? So this note was saying that if you have a solution to 1, 1, it will also be a solution to the equation above. And what was the equation above? It was just a linear combination, right? Are you following? I don't know if you're following or just nodding, but okay. And we can run this argument for every equation in 1, 2, right? Okay. And conversely as well, right? conversely as well. So, okay, tell me what the converse equation statement should be. So if x1 to xn is a solution to with a solution to 1, 2, then it is also a solution to 1, 1, right? I mean, this statement is basically saying it's a solution to 1, 2. Okay, this right? And this is how we get the theorem statement. So the theorem statement, theorem 1 says the following. So equivalent what is it? Systems have the same set of solutions. Linear equations have exactly the same set of solutions. Okay, so good. We managed to get our first theorem done. We understand the proof, hopefully. If something is not clear, go back, think, and you can also ask me if you have any questions in the next class. Okay, this is like one main thing that we wanted to cover. Right. Okay. So now what we're going to do is we're going to look at in the next section. So in the following discussion, we look at how one can produce an equivalent system. So starting from an arbitrary system, one can construct an equivalent system, which is much simpler, from which one can get the solution, to actually figure out what the solution to the set of linear equations. That is sort of the objective. Okay, so let's do that. Okay, so now we're going to look at, so this is section 1.3 in the book. It's called Matrices and Elementary Row Operations. So we're going to go really slow in the beginning to make sure that everyone's basically the foundation is sort of okay, and then we'll see how to pick up pace later. So for now, we're going to make the notation. Okay, so we make the notation brief. How we do this is basically by okay. So how we do this is by basically writing. Come on. Sorry about that. Okay, so the notation we're going to do use is the following. So we abbreviate. Do you have something to say, or? I mean, like I said, if you're feel free to read something else. Okay, just please don't talk among yourselves. That's the only request I have. Sorry, give me a second. The background is causing a little bit of a disturb. Let me fix that. Actually, one thing I wanted to ask you guys, maybe it's a good time to check quickly. So is it better like this, or do you prefer, is it clearer if I do it on a white background? So for example, instead of this, if I write on this side, let's see. Is this better? This is better? Okay, fantastic. So I don't have to deal with this. Okay, I'll change it next time. Okay, so for now, since we already started, next time. Oh, we started a new section actually. Maybe I could just start from the bottom. Okay, now let's do that. Let's create a new board now. Right, so Okay, so now we're going to look at section 1.3, like I was saying. So this is called matrices and elementary row operations. How do I get rid of this? Okay. Yeah, I'm sorry. I'm also still learning how to use this. The multitasking is a bit weird. Okay, so matrices and elementary row operations. You can also see the shadow now. Good. Okay, so here's the notation that we're going to use. So we're going to use, so we abbreviate, the system that we had. So system 1 as ax equals y. Okay, where a is the following. So it's a11, a1n, am1, amn. Right. X is, any guesses for x? Exactly. So x1 to xn or m? N. Okay. And y is, okay, let me, so I'm keeping the height slightly different to visually depict that, so you're multiplying like this, right? Something like that. So forget y. Oh. All right. And here A is called, so A is called the matrix of coefficients of the system. Okay. All right. Now, there are some remarks that the book makes here. So the first thing the book says is that, yeah, so here, for now, it's just a shorthand. So we look at the formal definition later of matrix multiplication. So matmult will appear later. Okay. So if you've not seen matrix multiplication in more serious detail, we can make a look at it later. And there's like this sort of pedantic comment which says that A is strictly speaking not a matrix. I mean, it's a representation. Okay, so it is a representation. And okay, so what a matrix is, so the definition apparently is that, so an M cross N matrix, you need to see this probably once in your life, so it's okay. Over the field F is a function A from I comma j, okay, where I is, oh shoot, so I is between 1 to m and j is between 1 to m. So because this was the number of rows, right? Number of rows, which was the number of y's, right? Is that okay? Okay, into the field. Scroll down. You can't see the screen below a certain threshold. Is that what you're saying? So you want to see more content, is what you're saying. You got it? Okay. Sorry. I wasn't sure what down meant. Like, you mean this is down or is that down? I wasn't sure the direction in which you okay. Okay, so like this is just notation, right? So okay, that's fine. And now what we're going to do is we're going to consider sort of elementary operations on these matrices. Okay. So the story now is consider elementary operations. So let's start with okay, and what these elementary operations are, they're basically just capturing linear combinations. And this is what we want to capture from. Okay. So here's an informal definition. I have done it. It's just that there's a lot of lag. Sorry. I was just sitting and waiting. What is happening?
Elements of the field are and doubles for
Elements of the field. No, the field is defined. That's fine. So what I'm defining is a matrix here. So matrix is a function from these indices into an element in the field. So for example, A of I comma j would be like the matrix entry. And row I, right, and column j. That is sort of what is being said. Is that okay? Did I answer your question? Did I misunderstand your question? Probably misunderstood your question. What is your question, set again? Elements of the field, I think of this as a subfield of complex numbers, right?
so it's not complex numbers.
It is from integers, right? I comma j. So these specify integers. So it's going from integers to an element in the field. So it's integers to say a complex number, or integers to a real number, something like that. Okay, sorry. I thought this was completely straightforward, but if you're seeing it for the first time, it's good to pause and make sure that you're following. It's nothing very complicated, right? Normally we just write a matrix as, rows and columns and we put some numbers in it. This is here, it's just saying it a bit more formally. It's saying that it is a function which is going from indices to a complex number. So a pair of indices to an element in the field. That's it. Okay, and I guess these things get important because when you go to infinite dimensions, then things can be a little bit more tricky, and maybe that's why they're going. Okay. It's a very minor point. Like you probably never have to worry about it in the course, but I thought I'd mention. Oh no. Wait, what? We only have 3 minutes? Really? Oh, okay. Yeah, we probably need. Okay, it's fine. It's fine. Let's keep at it. So in the last 3 minutes, let's quickly look at this informal definition of elementary row operations. Okay, so what is an elementary row operation? So informally, okay, so this is an informal definition. So intuitively, what we're doing is we are kind of building towards, the set of operations that essentially capture everything we want from linear combinations. So one thing that we can think of is as follows. So linear operations on, let me write it down more carefully, on M cross N, on an M cross N matrix A over F are defined as follows. Okay, so the first one is that multiplication of one row of A by a non-zero scale C. So that's the first one. Second one is, so is this fine? So you take one row of A. So, suppose A is like this matrix. This matrix, you pick one row, you multiply it with some scalar C, and that's it. That's the operation. Okay. That's the first operation. Second one is replacement of the rth row of A by row R plus C times row S. Okay. So what would this look like? So you replace the rth row. So suppose this is the rth row. Okay. And this is the S row, whatever. Okay. So what you're going to do is you're going to replace the rth row. So you're going to take this S. And so okay, let me just write it like this. So you replace this with R plus C times S. Okay, like the row. Something like that. Is that okay? So you take each element, you multiply it with the same element. Okay, and the third one is basically you swap two rows, interchange of two rows. Okay. Okay. So it's time. I shouldn't. So I'm strict about starting. So I should also be respectful of the ending time. So I think it's time. Let's stop here.